Hello, this is Pat Hindle, editor at Microwave Journal. It is my pleasure to welcome you to today's webinar on PCB materials and processing considerations for filter design, presented by John Coonrod, Technical Marketing Manager of Rogers Corporation Advanced Connectivity Solutions. Before we begin the presentation, let me cover some few items about the On24 platform. In the center of the screen, you will see a window containing the presentation. You may enlarge this to full screen if you want a better view of the slides. The window on your screen labeled Resource List contains a copy of the presentation, which you may download at any time. The webinar is being recorded and will be available for replay within about an hour from when we conclude today, allowing you to watch it again and recommend it to colleagues who are not able to join this live event. You will find a link to the recording in the events section of the Microwave Journal website. If you have any technical problems, please click on the yellow box with the question mark at the bottom of your screen. It will take you to a helpful user's guide. After the presentation, we'll have time for questions. If you'd like to ask one, just simply type it into the Q&A box on your screen. The first portion of this webinar will discuss multiple material properties which should be considered in modeling and simulation stages of filter design. Following, there will be several issues addressed that will relate to PCB fabrication and can influence filter design. Lastly, a simple yet effective concept will be discussed which allows very significant reduction of spurious harmonics for microstrip RF filters. Included in the discussion will be some modeled results of different filters and a comparison with the measured results. At this point, I'd like to introduce our presenter today. John Coonrod is Technical Marketing Manager for Rogers Corporation, the Advanced Connectivity Solutions Division. John has 30 years of experience in printed circuit board industry. About half of his time was spent in the flexible printed circuit board industry regarding circuit design, applications, processing, and materials engineering. The past 15 years have been spent supporting high-frequency circuit materials involving circuit fabrication, providing application support, and conducting electrical characterization studies. John is the chair for the IPC D24C High Frequency Test Methods Task Group and holds a Bachelor's of Science in Electrical Engineering degree from Arizona State University. So at this point, I will turn the presentation over to John.
Thank you. Welcome, everyone. We're going to be talking today about high-frequency materials and also printed circuit board considerations, PCB processing considerations for filter design. And the agenda is shown here that I'm going to go through. I'm going to talk about material properties first, and right up front, I should apologize that some of this is repetitive with some other presentations and webinars I've given, but I'm doing that purposely because these properties are actually very important for filter design, and also I'm going to talk about these properties a little different than things I've done on other webinars, and I'm really going to be talking about how they can impact specifically filter design. And then also go through some PCB fabrication influences, and then finally the last bullet there, composite materials to suppress spurious harmonics. That's going to give a pretty good overview of a certain type of filter. It's a microstrip edge coupled bandpass filter, and some tricks that you can do to really get a better performance out of it. So with that, let's go ahead and get started. And I want to talk about design decay first. And design decay is really a circuit property, even though I have it under the heading of materials properties. But excuse me, design decay is a circuit property, kind of like insertion loss is that we know that materials have an influence on insertion loss, but it depends on the design. Like microstrip compared to strip line is going to be different for insertion loss using the same material, but the material does have an influence. Same with design decay. Some of the terms I'm going to be using are listed here. So I'm mostly going to talk about relative permittivity in the sense of decay. So when I say decay, I mean relative permittivity or dielectric constant or epsilon sub r, E sub r, K prime. And then the design decay is actually an extraction method that we use by testing microstrip transmission lines using a differential phase length method. And it's actually a pretty simple method. Basically, we test a short length circuit and a long length circuit, and we measure the S21 phase angle, and from that we can extract the affected dielectric constant, and then using a field solver or other software we can find out what the dielectric constant is as the circuit perceives it. And that's dielectric constant of the substrate and also the effects of copper, and copper roughness does have an effect on that. There's 4 different dependencies for design decay listed here: frequency, substrate thickness, copper surface roughness, and circuit design type. I'm really not going to get in a lot of detail today with design decay just because of timing. I'm just going to hit the basics. But if you are interested in more details on this topic, we gave a webinar October 24th last year, and that reference is given here, and that will give you a lot more information on design decay. So going through the basics on this idea of design decay, first off, if you can imagine an electromagnetic wave propagating in free space and it encounters another medium, that other medium will be a higher dielectric constant, and higher dielectric constant is going to do several things to the electromagnetic wave, one of them being slowing it down. So higher dielectric constant means slower wave propagation, or slower wave means higher dielectric constant. But we've also found that there's other things that can slow the wave down besides the dielectric constant of the substrate. And one of them is copper surface roughness. And a rougher copper surface actually will slow the wave down. And it's a very simple experiment to do, which we've done several times, and that is you can build the exact same circuit on the same substrate using 2 different types of copper, one that's smooth and one that's rough. And the circuit that has the rough copper will have distinctly a slower wave, and the circuit will perceive the slower wave as a higher dielectric constant, even when the substrate is the same. And the chart given here is actually a good overview of this concept, I think, and it's an experiment we did several years ago where we used 4 mil LCP substrate, used the exact same material, same lot of material, tried to keep the material influences minimized, and then we obtained 4 different types of copper that had significantly different surface roughness, and we measured the surface roughness with a non-contact laser profilometer. And once we had a good measurement of the copper roughness of these 4 different types of coppers, we made 4 different laminates using the exact same substrate. We had circuits made, they're 50 ohm microstrip transmission lines, and then we tested them using the microstrip differential phase length method. And the results of that are the charts shown here, where the y-axis is the effective dielectric constant of the circuits, and the x-axis is frequency. And you can see some pretty distinct trends there, where the circuits that had the copper with the smoothest surface, and by the way, the surface I'm talking about is the surface between the copper and the substrate as we would make the laminate. So the circuits with the copper with the smoothest surface is the red curve, and that red curve is, those circuits were basically using copper that had a copper surface roughness about 0.5 microns RMS. And you can see the next curve up, it's a little higher effective dielectric constant, again using the same substrate, but a little rougher copper, 0.7 microns RMS, a little higher effective dielectric constant. And then the purple curve is a little higher, the blue curve is the highest. The blue curve is from circuits being tested using the roughest copper, which is 3 microns RMS. And there's a few things interesting here. One is you can see a big difference between the circuits with the smooth copper red curve and the circuits with the rough copper blue curve, about 0.3 difference in effective dielectric constant. And keeping in mind that this is the same substrate, there is no difference in the dielectric constant of the material itself. This difference in effective dielectric constant is related to copper surface roughness variation only. Rougher copper slows the wave down, and a slower wave is perceived by the circuit as a higher dielectric constant. There's also a thickness dependency to design decay, and this is an example of one of many experiments that we've done where we're basically used the exact same materials, same copper, same everything, and I made 2 different laminates, one thin, about 4 mils thick, another one thicker, about 30 mils thick. Sent the laminates off to have circuits made. We tested them again, 50 ohm microstrip transmission lines using the differential phase length method, and I averaged that from about 8 gigahertz to 40 gigahertz to get the design decay. This is not effective decay now. This is actually design decay, or the dielectric constant as the circuit would perceive it. I get a dielectric constant of about 3.95 on the thin circuits, and on the thicker circuits, about 3.68. And this is using RO4350B laminate, and if you would make even a thicker laminate on this exact same material, let's say 60 mils thick, you're going to get a design decay about 3.66, which is the number that is on our data sheets and product selector guide. And the 3.66 number is really the number where the copper surface roughness no longer impacts the wave velocity, so you're really detecting the intrinsic or the bulk dielectric constant of the material, which in this case is about 3.66. And if you want even thicker than that, instead of 60 mils, go to 90 mils. The design decay is still 3.66. 120 mils thick, 3.66. So basically, once the copper planes are far enough apart, the surface roughness doesn't impact the wave velocity anymore. And then you're really, again, detecting the intrinsic dielectric constant material, which is 3.66 in this case. And, of course, when it's very thin, in the case of the 4 mil, the copper planes are very close together, and now the surface roughness does impact the wave velocity significantly, and it slows it down. Slower wave means higher dielectric constant. So there is a thickness dependency. This is just kind of driving that same point a little bit further. These are 3 different circuit sets that were built on RL3003, which has a bulk dielectric constant of 3.0, used in standard ED copper, and the circuits that we're using the thinner laminate, which is the green curve, that's 5 mils thick. You can see it has a higher dielectric constant versus frequency curve. And also, again, the y-axis is dielectric constant as extrapolated from the differential phase length method. This is not effective dielectric constant. This is actually dielectric constant as a circuit would perceive it. So the green curve is the circuits made on the thin 5 mil RL3003 laminate. Blue curve is a little thicker circuits, 10 mils thick substrate, 20 mils thick is the red curve. And if we made something even thicker, about 50 mil, 50 thick, then that curve should line up pretty closely to the number of 3.0, because that is the intrinsic dielectric constant of this material. And once the copper is far enough apart, in the case of a thicker laminate, then that's really what you're detecting for the design decay. There's also a frequency dependency, and there's a material dispersion. Of course, there's different kinds of dispersion. There's transmission line dispersion, where strip line is less dispersive than microstrip. But in this case, we're really talking material dispersion. And what I mean by that is the dielectric constant will change with a change in frequency, within the frequency that we are testing anyway. But if you really go down to lower frequencies, you can see that the dielectric constant is, as the name implies, it's actually constant when you change frequency at the lower frequencies. Once you get up into the higher frequencies, a few megahertz up into the gigahertz range, that's when these dipolar moment relaxation starts having an influence, and that actually augments the electric flux, which causes the dielectric constant to change with frequency. So normally what we see in the range of frequencies that we test, we see a decrease in dielectric constant with an increase of frequency. And just to kind of prove the concept and kind of realize it's not related to the test method, I tested the exact same sheet of material with 3 different test methods and looking for that trend of lower dielectric constant as frequency increases. And first off, what I did was, on this one sheet of material, I did FSR testing, which stands for full sheet resonance test. And that test is, I'm able to test 2 different nodes, node 10 and 20. Node 10 is lower frequency, 20 is a little higher frequency, and I did see the trend that was expected, where I go from low to high frequency. I see a slight decrease in dielectric constant. The lower frequency is the red square. The higher frequency for FSR is the green triangle. So once that was tested, I sent off the copper-clad laminate to have circuits made, and circuits came back, and in this case, I made some ring resonators. And there's a 1 gigahertz ring resonator that's circled about in the middle of the chart, and then there's a 5 gigahertz ring resonator off to the right. And again, you can see when going from 1 gigahertz to 5 gigahertz, you do get that decrease in dielectric constant as expected. And then finally, the last test method was the microstrip differential phase length method, and that is the blue curve. And that's also obviously showing a negative slope, and that's really a decrease in dielectric constant with an increase of frequency. So using 3 different test methods on the same sheet of material, I get that trend where the dielectric constant decreases with an increase of frequency, and that's the normal trend for material dispersion. Excuse me. Where to find design decay? On our Rogers Technologies Support Hub website, we have software that can be downloaded or ran on one of our web pages, which is MWI 2018. The screenshot shown here is actually MWI 2017. We just recently upgraded that to MWI 2018. It's going to have the exact same screenshot as shown here. We've just upgraded that, added a few new materials, and was able to get rid of a few bugs too. So anyway, to get the design decay on any particular material with the software, you would select the material first and then select the thickness. And the software will know what surface roughness is used with that material and thickness. And then in this case, you would put in the frequency. For a frequency-dependent application, I put in 3 gigahertz, and then the design decay number and the box circle will show up, and that design decay number is basically the number I measured on microstrip circuits at that frequency with that thickness of material. So if you also have a different application that could be a very wideband application, or maybe it's a digital application, or if you're just trying to get characteristic impedance, then you can click on a different option here that is decay value for characteristic impedance, and then click on the material you want, the thickness you want, and it will give you the proper design decay for that. So the software can be used to find the design decay for any of our materials at different frequencies, or also if it's a wideband application or high-speed digital or characteristic impedance, you can use this option. So let's talk about anisotropy. Most of the materials used in the PCB industry are anisotropic, and what I mean by that is the dielectric constant is not the same on the X, Y, and Z axis of the material. That's very common, actually, for materials used in the PCB industry. And the reason that happens is a little complicated, but in the basic sense, it's really due to electric susceptibility being different on different axes of the material. And I've given a mathematical tensor here that kind of describes that, and I'm not really going to get into details there. But normally what we do, we assume that the diagonal elements here in the tensor is actually what is of interest, and the non-diagonal elements we usually assume to be 0, which is normally a pretty good assumption. And on the diagonal elements, this is really X, Y, and Z axis dielectric constant. Usually the X and Y are relatively close to each other, and the Z-axis can be very different from the X or the Y. So a lot of times we will measure the XY plane and then compare that to the Z-axis. And there's a few reasons for that. One is the measurement is very difficult to measure the X-axis separate from the Y-axis. And there's easier test methods that are a little bit more accurate, too, to measure the XY plane by itself. So a lot of times we measure the XY plane of the material and then the Z-axis of the material to understand the anisotropy of it. Now, for filter design, anisotropy can be a big deal. And in the case of circuit features that are transmission lines or stubs or something like that, a lot of times anisotropy is not considered, and many times that's okay. But for a lot of filter designs that are edge-coupled, such as microstrip edge-coupled filters, then anisotropy can be a pretty big deal. And actually, my previous topic, copper surface roughness, that can also play into accuracy for modeling filters. So anyway, back on anisotropy, what I've shown here is 3D views of differential pair microstrip transmission lines. And I'm looking at different modes here, even mode and odd mode. And even mode, most of the electric fields are in the substrate, a little bit of fringing at the edges, of course. And odd mode, you also have electric fields in the substrate, but you also have some electric fields fringing in air. And air is the lowest dielectric constant, of course. So you can see some differences in the affected dielectric constant due to the fields using different amounts of substrate or air and even an odd mode. Also, I showed there something that can be a concern sometimes called the glass weave effect. A lot of laminates have glass weave as a mechanical reinforcement layer. And in this case, I'm showing odd mode in the middle picture, having electric fields that are interfacing with this glass weave. And then the right picture, the picture on the right there, odd mode where the electric fields are not interacting with the glass. That can actually make a difference with the odd mode because glass is a higher dielectric constant than the resin system typically. So this is something I'm really not going to talk about much today, but the glass weave effect can have an influence if the circuit features line up to the glass patterns in a very specific way. So it's a little unusual, but it does happen from time to time. So anisotropy really should be considered with filter designs that are using coupled features, such as, again, microstrip edge coupled. And I'm going to talk about that type of filter later on. And the general rule of thumb would be that the anisotropy in general is less of an issue on materials that are non-glass reinforced. And it can be more of an issue with glass reinforced materials. And then also, higher dielectric constant materials typically have more anisotropy. And I've given some information here on some different materials that we've measured in the Z-axis and also the XY plane using SPDR, which is split post dielectric resonator. And you can see that the RO3003 materials has a dielectric constant in the Z-axis that's pretty close to the dielectric constant in the XY plane. So it's pretty close to being isotropic. But as you go up in dielectric constant 3006, you can see there's a bigger difference between the z-axis and the xy plane. So higher dielectric constant is usually a little more anisotropic than lower dielectric constant, just general rules. And then also the 3003 materials compared to the RO3203 materials are basically the same materials, except that 3203 has glass reinforcement and the RO3003 does not. And you can see that the material with the glass reinforcement, the 3203, does have a little more anisotropy than the material that does not, the RO3003. So this is a output of a Sonnet model that I ran. So I ran a model in Sonnet software, and we have the professional version of Sonnet software that does account for anisotropy, and also it has a very good routine that accounts for copper surface roughness. And this is really showing the exact same filter design. I changed nothing at all in the filter design except that I had anisotropy on in one model, and another model I had anisotropy off. And the difference in this case had a center frequency shift of about 70 megahertz, and there's actually even more of a shift out at the spurious mode out a little bit higher in frequency. But really, 70 megahertz shift for some filters may not be a big deal, and in other cases, 70 megahertz shift could be a really big deal. So considering anisotropy for a particular design is a very safe thing to do. Let's talk more about material properties, CTE and TCDK. CTE is coefficient of thermal expansion, and that's a property of a material, and that's basically how much the material is going to expand or contract by heating and cooling. And the ideal number would be to match copper. So if the substrate CTE was the same as the copper CTE, then that means everything is going to expand and contract the same as the circuit is heated and cooled, and that's a good thing. So copper CTE is about 17 parts per million per degree C. And as a general rule of thumb, most materials to be robust in different type of thermal processes should have a CTE of about 70 parts per million per degree C or less. And then for TCDK, thermal coefficient of dielectric constant, that's another property that all materials have, and unfortunately this one is sometimes overlooked, but that's really how much the dielectric constant will change with a change in temperature. And again, there's materials will have different type of TCDK behavior depending on the formulation, and a general rule of thumb is the TCDK should be about 50 parts per million per degree 50 parts per million per degree C or less. An ideal would be 0. Actually, that would be no change in dielectric constant with a change in temperature. And I'm given a chart here, actually, of several curves that's showing the behavior of TCDK for several different materials used in the high-frequency PCB industry. As a sanity check, I threw in there FR4, and FR4 is not really a high-frequency material, of course, and it's not formulated to have a good TCDK, so I wanted to give you an example of what a bad TCDK looks like, and that's the brown curve. That's FR4. The other curves are actually pretty well behaved for TCDK. You can see some of them have a little transition around room temperature, and that's pretty normal for PTFE. However, if the PTFE substrate has the proper formulation, ceramic particles or ceramic filler that is the right type of ceramic filler, and everything's done right for the formulation, you can actually minimize that room temperature transition and have a very good TCDK. Actually, the dark blue curve there is RO3003, which is a PTFE material, but it has also got the proper formulation to where it's almost ideal. And ideal would be 1.0 on this line because this is normalized dielectric constant at 25 degrees C room temperature. So you can have PTFE materials with very good TCDK, dark blue curve being the RO3003 shown there. Let's talk about some fabrication influences. So copper plating thickness does vary from circuit to circuit, and that's just the nature of the beast for making circuits. And on one panel of multiple circuits, if you were to check, you can see some variation of copper plating thickness from one circuit to another. And of course, batch to batch, you're going to see differences too. That's just kind of the nature of the beast. And in the cases for RF structures that are not coupled, like transmission lines or stubs or something like that, the copper plating thickness doesn't make too much difference. It does make a little difference in RF performance, but not a lot. But anything that is coupled features, that's where the copper plating thickness can make a pretty big difference. And depending on the design, it can be pretty significant, and in other cases, maybe not. But being that a lot of filter designs are using coupled features, I wanted to talk about the variation of copper plating thickness. And basically for a coupled transmission line, which I'm showing here, is a microstrip coupled transmission line. If you can imagine thicker copper, that means that the conductors are taller, and now you have more area between the sidewalls of the coupled conductors, which means there's going to be more coupling in the air, and air is a low dielectric constant, obviously. As opposed to the same circuit with very thin copper, now the conductors are not as tall, and the sidewalls of these conductors have much less area, and you have less coupling in air. And this coupling in air will make a difference in effective dielectric constant and phase response, and it can make a difference in insertion loss as well. So I did a study to kind of prove this point. And what I did was to minimize the effects of materials, I used the same sheet of material, which in this case was 10 mil RO4350B. I had a 24 by 18 sheet. I cut it in half, and one of those half sheets went off to have circuits made with thin copper plating, and the other half sheet went off to have circuits made with thick copper plating. All the circuits on both these half sheets were the same design. I had tightly coupled grounded coplanar waveguide, and I had loosely coupled grounded coplanar waveguide. The tightly coupled grounded coplanar waveguide means that the space between the ground signal ground conductors is a small space, and the loosely coupled is a wide space. And what I'm showing here from pictures is the tightly coupled grounded coplanar waveguide. So on the signal plane, the top copper layer, it's a ground signal ground configuration. And this particular one has what I would call the ID is W18S6. And what I mean by that is W18 is the width of the conductor, so it's 18 mils wide conductor, and the space between the signal conductor in the middle and the ground planes on both sides is 6 mils. So it's tightly coupled. The pictures on the right are the tightly coupled grounded coplanar waveguide with thick copper, about 3 mils thick. Pictures on the left are the same design except using thinner copper, 1 mil thick. And I went off and did insertion loss testing, and this is a result of that. And what I found was there's a pretty distinct difference for the RF performance. And in this range of frequencies, by the way, I ensured that the return loss was very good. I had to have at least 15 dB or better return loss, and in reality, all these I think were better than 17 or 18, so it's pretty good return loss. And what I found was the circuits with the least amount of insertion loss were the circuits that had the widest conductor and also the thickest copper. So that kind of makes sense to me. Wider conductor means you have less conductor losses, and also having thicker copper means that you have more coupling in the air, and air is the lowest loss medium there is. Now, in contrast to that would be the circuits with the most loss, which would be the W18S6 thin copper. And that blue curve is the most lossy of all these circuits, and that's using the most narrow conductor, so you have more conductor losses. And also the copper is plated thin, so you do not have the benefit of air being coupled more effectively. And again, back on the notations, the W21S12 that has the lowest loss, that means the conductor width was 21 mils wide, and the space between the signal conductor and the neighboring grounds is 12 mils, so that's loosely coupled. And then I also did the same kind of testing in regards to phase response, where I measured the phase angle, and then I figured out what the effective dielectric constant was. And the formulas I used to do this are shown to the left. It's pretty simple. These are just phase response formulas, the top one. And then I adjusted the formula to account for circuits at 2 different lengths, which is delta L, a short length circuit, a long length circuit. And then I finally get the effective dielectric constant out of it. And the effective dielectric constant is really just measuring the delta phi, the phase angle, S21 phase angle at frequency F, and accounting for the difference of length, delta L, and I get the effective dielectric constant at that frequency. So that's what I did, and you can see on this chart that we got a pretty interesting response where we see a pretty big difference in effective dielectric constant with these circuits. Now, keeping in mind, this is the same sheet of material, and you can see there's a difference of about 0.3 in the effective dielectric constant just due to the difference of the copper plating and the tightly coupled or loosely coupled design. So thinking this through, the way I was thinking about this intuitively is the green curve is W18S6, so that is the circuits with the tightest coupling, and it also has the thickest copper. So now you have electric fields that are in the coupled areas that are using copper that's thick, so that means the sidewalls of the conductors are very tall, and also they're close together. So you're using the air more effectively, and air is the lowest dielectric constant material, so you're going to have the lowest effective dielectric constant. And then on the opposite end of that is the W21S12 thin copper, and that is loosely coupled. S12 means a large space, so it's loose coupled, and also the copper is not thick, it's thinner, so you have less coupling in air, and you do not have the benefit of the lower dielectric constant of air. So again, this is using the exact same sheet of material, and I can see a difference of 0.3 in effective dielectric constant, and that's pretty significant, especially when you're talking about filter design. Also, if you just to compare the same designs only with thick and thin copper, we could look at the green curve and the blue curve, and that's W18S6 thick copper is the green curve, thin copper, blue curve, and there we get a difference of 0.1 in the effective dielectric constant. And again, remember, this is the exact same sheet of material, just the copper effects only made that difference. The copper effects in this case being copper thickness changing. So that's enough for that topic, I think. Let's move on to final plated finishes. We've done a lot of studies on this topic as well, and there's a couple of things I wanted to point out. Again, being that a lot of filters have edge-coupled features, I wanted to talk about that and make everyone aware that edge-coupled features usually have more losses and are impacted more by the final plated finish than a single-ended transmission line like a microstrip. So the left picture is a cross-sectional view of a microstrip transmission line, and it's showing the fields. And also I wanted to point out that at the very edges of the conductor where it meets the substrate, there will be high current density there. And as the final plated finish is plated in that area, the final plated finish usually has less conductivity than the copper. It's not as conductive. And because of that, it increases the conductor losses. And it's really an edge effect at the edges of the conductor. So a short link circuit is not going to be impacted too much by this final plated finishes for insertion loss. However, if it's a longer circuit, these edge effects kind of add up. They accumulate over the length of the circuit, and then there is going to be more insertion loss due to this edge effect for the microstrip. Now, in the case of the grounded coplanar waveguide, the circuit shown to the right there, that's a cross-sectional view of that with some drawing of the fields. And in this case, the final plated finishes actually affects the fields much more because you have coupling between the ground signal ground on the top copper layer, and now there's actually 4 layers of the plated finish that's actually affecting the RF performance. And in general, when you compare a microstrip circuit to a grounded coplanar waveguide circuit, you will see more losses on the grounded coplanar waveguide circuit because there's basically 4 layers of the final plated finishes that these electric fields are interfacing with. So I did a study to prove this concept too, and here I used the same material for making the microstrip circuits and the grounded coplanar waveguide circuits. And the circuit material is 8 mil RO4003C, and the chart on the left are the microstrip circuits. The chart on the right is the grounded coplanar waveguide circuits. The red curve is circuits built on bare copper, and the blue curves are circuits built with ENIG, electrous nickel immersion gold. And nickel is about 1/3 the conductivity of copper, and because of that, it's going to cause more conductor losses and ultimately more insertion loss, as shown here. So the chart on the left showing microstrip transmission lines, bare copper curve red and ENIG blue curve, there's a difference of about 0.5 dB per inch at 50 gigahertz. And that same exact material is shown on the right in a configuration of the grounded coplanar waveguide, actually tightly coupled grounded coplanar waveguide. And there the difference between the bare copper circuit red curve and the blue curve with ENIG is about 1.2 dB per inch. So the grounded coplanar waveguide circuit has much more losses due to the ENIG than the microstrip circuit when using the exact same materials. Now, in the case of filter and filter designs that are edge coupled, this can be a really important item to think about. And then talking about some other plated finishes quickly, this is another study we've done, and we got a lot of information on different plated finishes. This is using a pretty thin circuit, 5 mils thick. It was RT Duroid 6002 laminate, used very smooth copper, rolled copper, and the reference curve would be the light blue curve that is the bare copper curve, and there's also some other blue curves in that same area, and I left them that color purposely because, to me, they're all acting the same pretty much. So the bare copper circuit, the reference, the other finishes that are very similar is OSP and immersion silver, or basically OSP, organic solderability preservative, that and immersion silver really does not contribute to insertion loss, doesn't make a difference to insertion loss compared to a bare copper circuit. And then the brown curve is solder mask. That increases insertion loss more, obviously. Immersion tins, green curve, NEPIG, yellow curve, and red is ENIG. Now, ENIG is the most lossy one, and that's usually how it is on a lot of these studies that I've done. And I'm not talking bad about ENIG. ENIG is actually a really good finish, and it's used a lot in the industry. It has a lot of good purposes. However, ENIG does cause more losses, and it's due to the nickel. So as long as the designer accounts for the losses due to ENIG, then that's fine. But that's definitely something to consider. Now, another thing that came out of the study that I thought was interesting is there is a phase response difference to final plated finishes. To begin with, the solder mask, which is not a final plated finish, that's the orange curve, that's the higher decay. That is going to increase the dielectric constant, of course. But these other curves here are metals, so they are different finishes that we just talked about. And the yellow curve is ENIG, and that has the biggest change from going 1 gigahertz to 10 gigahertz. And that range of frequencies is really where you're seeing the skin depth change, of course. And the skin depth with a composite metal like copper, nickel, gold, that's really what it would be for ENIG. That's going to be changing as you go up in frequency at skin depth well. And where this came into play was where I was helping a customer with an application about 2.5 gigahertz, and they were having problems from circuit to circuit, having variation. It turned out that the ENIG, that nickel layer of ENIG, was actually varying in thickness a pretty good amount. And that variation of nickel was actually causing the phase angle to change some. And that was causing a problem. So this is one of those topics that I don't run into very often. And usually at higher frequency, it doesn't matter that much, as you can see here. But at lower frequencies, 1 gigahertz up to around 5 or 6 or 8, then that can matter. It can make a difference on the phase angle, these different plated finishes. So solder mask, I'll talk about that briefly. Solder mask is typically not used in filter design that are edge coupled, and it can be done, but you have more inconsistencies when you do that normally. So solder mask is going to have some more variables than a circuit without solder mask, obviously. So some of these variables would be that the solder mask thickness is going to vary from circuit to circuit. And if it's a coupled circuit, edge coupled circuit, the solder mask between the coupled conductors, if that varies in thickness, you can imagine that's going to have an impact on RF performance, and it will. And there is some normal solder mask thickness variation circuit to circuit. Also, TC-decay, solder masks are typically not formulated to have good TC-decay, so the decay of the solder mask itself can change with temperature pretty significantly, actually. And then solder mask is not well controlled in formulation for decay. That's pretty much a true statement. The dielectric constant of solder mask does have some normal variation, but it's not really controlled, so that's another variable possibly. And then finally, moisture absorption can be a pretty big concern with applications that are out in the field where the circuit is being exposed to different levels of humidity. A very humid day one day, dry another day, that could make a difference on the moisture absorption in the solder mask, where the solder mask would absorb more moisture or less. And that difference in moisture will make a difference on the phase response of the circuit and the insertion loss as well. Here's a couple of charts that I'll talk through real quick. On the left is insertion loss, and on the right is a microstrip bandpass edge-coupled filter. They're using the same materials, 20 mil thick RO4350B laminate. On the left, the blue curve is the bare copper circuit, and the green curve is the solder mask. On the right, the brown curve is the bare copper circuit, the solder mask circuit, and the blue curve is the bare copper circuit. And you can see there's a little frequency shift there, and that's because the solder mask will increase the effective dielectric constant, and that will lower the center frequency. Also, if you look at the losses and try to compare them, the chart on the left is in dB per inch, and the chart on the right is just dB. And if you were to make a few assumptions here to try to convert the dB of the filter to dB per inch, what you'll find is the filter has much more losses at 3 gigahertz than does the transmission line. And that's because you have the coupled features used in the solder mask, and the solder mask does have a higher dissipation factor. Normally, solder mask has a dissipation factor around 0.015 to 0.025, so it's relatively lossy. Now on to using composite materials to suppress various modes or various harmonics in microstrip edge-coupled filters. Now, these spurious harmonics, basically they're harmonics that are not desired, and they can cause problems with isolation in the stop band. They can cause a lot of problems in a lot of different areas of the filter. And to begin with, these spurious harmonics are kind of natural by the design for edge-coupled filters. So edge-coupled filters using open-ended resonators that are half wavelength. The harmonics are usually even order, so it's usually 2F0, 4F0, 6F0. And F0 is the center frequency of the resonator or the filter. And then for edge-coupled filters using shorted resonators, like quarter wavelength, then those harmonics are usually on the order of 3, so 3F0, 6F0, on and on. And there's a lot of different things you can do to suppress these spurious harmonics. And IEEE Explorer website has a lot of good papers on this. But one thing that can be done and is very well known is if you can equalize the phase velocity and even and odd mode of the coupled filters, that will make a big difference in suppressing these spurious harmonics. Now, the reason the phase velocity is different in even and odd mode is really due to how the electric fields are used in the circuit structure. So in even mode, most of the electric fields are used in the substrate for dielectric constant, and in odd mode, the electric fields are also using the substrate, but also there's some coupling in air, and air, of course, is the lowest dielectric constant, so the odd mode overall is going to have a lower effective dielectric constant than the even mode, and a lower effective dielectric constant means a faster phase velocity, so the odd mode will have a different phase velocity than the even mode. And to implement this concept that I'm going to show in the next few slides is actually pretty easy nowadays because I see so many RF printed circuit boards that are multi-layers, and a lot of these multi-layer printed circuit boards are hybrids, which means that they're using dissimilar materials in the multi-layer stack-up, and they do this for a lot of different reasons. But I've given an example here of six copper layer circuit on the left and on the right. They're both the same 6 copper layer circuit. The one on the left is using more standard materials where we have high frequency materials for copper layer 1 and copper layer 2. And then the materials below that would be FR4 cheaper materials, and those are usually used for layers where the RF performance is not really critical. And then that same construction basically can be made with this composite concept that I'm going to show on the right cross-section, where the top copper layer and the copper layer just beneath there will be the microstrip, and that's going to use 2 different materials. One will be a high-frequency laminate, and the other will be a high-frequency prepreg, and they will have 2 different dielectric constant and different properties to make that composite material. But the multi-layer structure itself is pretty easy to make, whether it's a composite microstrip or a standard microstrip, standard being on the left, composite microstrip being on the right. So just going down this path a little bit more, thinking about this, here is some cross-sectional views of even and odd mode of circuits that are microstrip coupled and using composite materials with high dielectric constant. That's the epsilon sub r high, and epsilon sub r low is the lower dielectric constant. So the materials closest to the signal plane is the higher dielectric constant. The materials closest to the ground plane of the bottom is the lower dielectric constant. And you can see that the electric fields, and actually what I have drawn here is more capacitive lines, but still representative of electric fields. In the even mode, you can see that the electric fields are mostly using the z-axis or thickness axis dielectric constant. In this case, it's going to be a composite dielectric constant made up of the high and low dielectric constant of the materials. And in odd mode, you have that same situation, but you also have coupling between the 2 conductors. And that coupling is going to have some influenced by the high dielectric constant material and some influenced by the low dielectric constant of air. So I did a study on this to prove some concepts, and I'm going to show you some models and some measured data. And what I did was use the exact same circuit design, same filter design, but I used 2 different types of structures. One was a microstrip that was just simply 2 copper layers, and it was using 25 mil thick R2 Duroid 6010.2 LM laminate. That's the standard construction. And then I used a composite construction that was using that same laminate, 25 mil RT Duroid 6010.2 LM laminate plus 6 mils of 2929 bond ply. And that bond ply has a dielectric constant of about 2.9. That's the design decay. And the design decay for the 6010.2 LM material has a design decay of about 10.7. So there's a big difference in dielectric constant here between these materials. Now, if you do the right thing with the right combination of dielectric constant and the right thicknesses, you can actually get the phase velocities to get very close to equalizing, which will help to suppress those spurious harmonics. And if you want a little more information on this, that is actually a very rigorous treatment of this subject. It's an excellent paper that's shown here by James Gilb and also Dr. Constantine Balanis, who I have a great respect for. This is one of his papers that he did, and both of these gentlemen did a fantastic paper here. But really what it is, it's going to give you a lot more details of how to juggle the different dielectric constant and the different thicknesses to minimize the differences in phase velocities between even and odd modes. So I did some modeling, and this is a result of some of that. And what I did to begin with was I used a simple microstrip edge-coupled transmission line, and I put that into the Sonnet software. And from that, I got the effective dielectric constant in even mode, effective dielectric constant in odd mode, and then I used some pretty simple formulas for phase velocity, and that's shown here below. And from that, I tried to find out what the phase velocity was of even and odd mode, and I altered the construction until I got a pretty good match between even and odd mode phase velocities where they were pretty close to being equal. And for the study, what I decided to do was use, in the table of information here, ID1 and ID3. So ID1 is the control circuit, basically. That's just the standard microstrip transmission line, or actually in this case it'd be a filter, used in 25 mil thick RT Duroid 6010.2 LM. It's not a composite, that's just a standard laminate. And then ID3 is the construction I just described on the previous slide, where it's 25 mil thick high decay material and 6 mil thick low decay material. And it gives me a pretty close match to phase velocity. And actually ID2, if you look at the data, is pretty close as well. But I decided to go with ID3 because I know the 6 mil 2929 bond ply will actually reduce in thickness slightly during the lamination. And now I know it's going to end up being a little bit less than 6. And if you look on that chart there, if I go from 6 down to 5, that's going in the right direction. That's getting closer to 0, or the 0 difference between even and odd mode phase velocity. So the filter design itself was centered at 2.5 gigahertz. I used a Chebyshev transfer function with a 0.1 dB passband ripple. And also to show the differences in coupling, I decided to design this filter with 2 different bandwidths. And one filter design had 180 megahertz bandwidth. Another filter design had 440 megahertz bandwidth. And just due to that bandwidth, you will get quite a difference in coupling, where the 180 megahertz bandwidth filter will have loose coupling, and the 440 megahertz bandwidth filter will have tight coupling. So I wanted to show this concept with loose and tight coupling, so that's why I did that. And what I did in my experiment, I did not build a multilayer, even though you could very easily. I kept it pretty simple, and I just made very simple 2 copper layer microstrip circuits, one being the standard material shown on the left, bottom left picture, and the other one being a composite that I put together with the 6 mil bond ply with the 25 mil high frequency, high decay material. So this is a model of 2 of these filters, and one of the filters is using the standard material. That is the pink or magenta curve, I guess, and that is ID number 1. That's using the standard material. That is the bandpass filter centered at 2.5 gigahertz with a bandwidth of 180 megahertz. And then the other filter, same exact design, except using the composite material. That's the blue curve. You can see that the spurious harmonic out to the right there at 4.9 gigahertz, there is a pretty good reduction. So the pink curve or magenta curve at 4.9 gigahertz has a spurious harmonic at a level of about 6.5 dB. And then the blue curve that's using the composite material has a spurious harmonic about 36.1 dB, so a pretty big reduction in that spurious harmonic at 4.9 gigahertz. Now looking at that same type of idea, except the tightly coupled wider bandwidth filter, 440 megahertz bandwidth, the standard material, you can see that is again the pink or magenta curve, and the blue curve is the filter using the composite materials. And again, we see a pretty big difference in the spurious harmonic going from about 8.9 dB down to almost 40 dB at the 4.9 gigahertz. So I made circuits, tested them, and I will show a screenshot of these filters being overlaid. And to begin with, this is the 180 megahertz bandwidth filter, and it was centered at 2.5 gigahertz. And you can see the spurious modes off to the right there. The brown curve is filters using the standard material. The blue curve are the filters using the composite material. And we've got a pretty big difference in the harmonics there. And in the case of the standard material, it was about 9 dB or so at 4.9 gigahertz. And the blue curve at that same frequency, you can see, is actually below 50. So we got a very big difference in the spurious harmonics. And that's a good thing, obviously. And the reason also, the other thing I wanted to point out is if you compare this closely to the sonnet model, you will see a difference between the sonnet model and the measured results. And that's not due to an issue with the sonnet model. That's due to me not optimizing the sonnet model compared to the measured circuits. So the sonnet model was based on the nominal design, and the circuits has some variation, of course. So the conductor width was not exactly what the nominal design was. The substrate thickness was not exactly what the nominal design was. So if I would have tested these circuits and then microsectioned and put in the exact dimensions into the sonnet model, I'm sure the sonnet model, in fact, I've done this before in other designs, will match this very closely. But anyway, there's some real-world influences involved with the measured results I'm showing here that are a little different than the sonnet model. Same idea again, except this now is a comparison of the filters with the wider bandwidth, 440 megahertz. The standard material is the brown curve. Blue curve is the composite material. You can see there's a big difference in the reduction of the spurious harmonic at 4.9 gigahertz. It's a difference about 8 dB all the way down to about 45 dB. So that's really a pretty good reduction of that spurious harmonic. And then lastly, I wanted to point out the fact that whenever you do this trick with the composite materials, the overall composite decay is going to be a little bit lower because we inserted this bond ply that has a lower dielectric constant. And of course, a lower dielectric constant is going to make your features get larger. So I wanted to give you reference for how much difference there was in physical size between the composite materials, the filters that use the composite material, which is the green dimensions, and then the red dimensions are the filtered dimensions for the filters that we use in the standard materials. So yes, there is a difference in size, and the composite material trick to minimize spurious harmonics will cost you a little bit in real estate, but not a heck of a lot. But that is something to be considered. And then finally, I wanted to invite you to become a member of the Rogers Technology Support Hub. We've got a lot of good information in there. We're really kind of proud of this. We have impedance calculators. We also have a decay calculation software that you can get. We also have Rod's mobile app on there. We have a lot of calculators. They're usually pretty basic calculators, but they're actually very helpful for electrical and different thermal issues. And we also have a place on there you can ask an engineer, so you can type in a question and it will go off to an engineer in your region. And we've got a lot of white papers, and we have some papers from trade shows in there, and also many videos. A lot of these videos are kind of short videos, introductory kind of videos to different topics, and some of these videos are much longer, sometimes recorded at some trade shows that we present at. So lots of good information there, and that's all I have. It looks like I have a few minutes for questions.
Great, John. Excellent presentation. I love the way you always present nice, convincing data there. Thorough. So first question is, what's the difference between the actual dielectric constant and the dielectric constant as the circuit perceives it?
Yeah, that's a good one. And it really depends on those different dependencies. So if it's a very thin circuit and the copper's rough, there's going to be a pretty big difference between the bulk decay of the material and as the circuit would perceive it. If it's a thin circuit and the copper is very smooth, then that doesn't slow the wave velocity much. And then that means the dielectric constant of the circuit and the bulk dielectric constant is not going to be that different. So it really depends on the circuit construction. Thin is going to have a bigger influence on due to the copper surface roughness, and it's going to be a different number in a thin circuit than a thicker circuit. Thicker circuit where the copper is farther apart, the difference between the bulk decay and the decay as the circuit would perceive it is going to be pretty close to the same on a thicker circuit, to be honest.
Okay, great. Next question. Is it possible to get thermal data of the material to run electrothermal simulation with accurate information?
Yes. We do that, and it's kind of a tedious thing for us to do, to be honest. And because of that, I don't do it a lot. But I do have that on some of our materials and some configurations, and I have done that with some filters too. And it's always interesting to look at filters with a thermal image, especially if you sweep the frequency. It's kind of neat because the filters have a area that's a stop band and then the pass band. And if you're down in the region of the stop band, you can see a lot of heat coming in on the feed line, and the first element of the filter really glows, and the rest of the filter is nice and cool. And then if you look at the thermal image in the pass band, where the frequencies in the pass band, you can see the whole filter distribute the heat pretty evenly, so it's kind of neat to do. But anyway, I guess back to the question, I do have some thermal images related to some circuits. Some of those are transmission lines, some of those are couplers, some are filters, but I don't have a lot of information. So whoever's interested in that, I would ask you to go ahead and email me, and I'll be happy to share what information I do have.
Great. Next question, how can you reduce the effect of the solder mask?
That's a tough one. I guess, obviously not have a solder mask, but that's the easy way to answer. But if you have to have a solder mask and trying to reduce that, I've looked at different solder masks, and from what I can see, there's some small differences that you can find with different solder masks. And in a general sense, there's two kinds of formulations for solder masks. There's an acrylic base and an epoxy base. And what I found was the acrylic base actually seemed to be a little more consistent, and they actually have a little better dissipation factor. And also color matters, believe it or not. So the pigment that's used to color the solder mask actually has an effect on, I think it's really the ionics within the solder mask, and it has an effect on losses. And as I remember right, blue, believe it or not, is a little bit better than the other colors. And that's all very small numbers, to be honest. But for trying to minimize the effects of solder mask, there's no good way to do that I know of, to be honest, except just for these little changes I just talked about. Acrylic's a little bit better than epoxy base. Blue might be a hair better than the other colors. And then if you had thinner, consistent solder mask, that's going to be better. But the consistent thickness would be the trick there. So I guess I really don't have that good of an answer for the solder mask question.
Well, that's really interesting that the color affects it slightly. Next
question, it does very little, but it is there.
Well, you can measure it, so that's something. What techniques are used to measure decay in different frequency ranges with almost equal precision?
Well, that's a good one, too. So what I've shown in this presentation today, that what we do for design decay is actually use the microstrip transmission lines, and it's the differential phase length method, and that's a good approximate number for a wide band dielectric constant across frequency. But I see that more as an approximate test method. I personally think resonators are far more accurate, and it depends on the type of resonator. Like a ring resonator, I think is very accurate at lower frequencies, but when you get to higher frequencies, it gets to be a little more problematic because of the copper surface roughness effects actually causing some issues, and also the gap coupling between the feed line and the ring resonator. If you have tall copper or a short copper, as in copper thickness variation, that also influences the resonator. So in general, I think resonators are more accurate for determining dielectric constant, but you have to be very careful what resonator you use in the design of the resonator. What we do, though, normally is the microstrip transmission line testing differential phase lengths to give an approximate dielectric constant versus frequency curve. But again, resonators, I think, are a little bit more accurate. I have some interest in SIW resonators as well, because that might be a little more accurate too, but I just haven't put a lot of work into that yet.
Next question, is copper roughness better or worse with electroplated versus rolled?
Yeah, again, just to make sure everyone knows what I'm saying, the copper surface roughness I'm talking about is not the air side of the circuit or the laminate. It's actually the copper at the interface between the copper and the substrate as we make the laminate. The rolled copper is almost always much smoother than ED copper, and there's a lot of different ED coppers out there. There's reverse treat, and there's all kinds of different types of ED copper. And in general, for copper surface roughness, rolled copper is the smoothest, reverse treat is a little bit rougher, and then ED is the roughest. And there's a pretty wide range of roughness values when you really look at these different coppers too. But generally speaking, rolled copper is the smoothest.
Next question, what's the main difference between decay in the XY plane and the Z-axis of a substrate?
I'm sorry, say that again, please.
What's the main difference between decay in the XY plane versus the Z-axis of a substrate?
It depends on the materials, but in some cases it can be due to the glass weave. A lot of materials have layers of woven glass fiber, and that glass weave can make the dielectric constant different in the XY plane as compared to the Z-axis. And then sometimes it's actually the material itself. So there are some materials that are more anisotropic. In fact, I gave an example of RL3006 that does not have glass weave in it, but it is anisotropic. And the reason why is because the ceramic particles that we use to adjust dielectric constant, TCDK, and other things, those ceramic particles are not spherical. They do have a shape to them, and I would say it's kind of a football shape, so to speak. Not really that way. It's kind of random, but it's kind of chunky. And what happens is when this material is under high pressure in a gel state, when we're making the laminate, these particles do have a natural orientation. They want to orient in one direction more than another. And because of that, you do get a different directionality or anisotropy in the x-axis or y-axis compared to the z-axis. So it kind of depends on the material and the formulation and the glass and no glass and the ceramic particles. So there's several different things that actually come into play there.
Next question, what's the best Rogers material for millimeter wave applications, like for antennas and filters?
Yeah, that's pretty easy because for the last couple of years we've been just buried with demands on RL3003 mil for 77 gigahertz automotive radar, and that material works fantastic at millimeter wave frequencies. However, we do have other materials that work extremely good at millimeter wave frequencies. The RT Duroid 5880, the CLTE AT, CLT MW is a new material that has excellent performance at millimeter wave and being adopted more and more. So those are some of the materials we have, but we actually have a lot of materials that work very well at millimeter wave. And I would say just by default, the RL3003 is the material of choice for 77 gigahertz automotive radar, and it works very good at that. We also have a thermoset. The RL3003 is the PTFE material. We also have a thermoset that's a little bit easier for circuit fabrication that also works very well at millimeter wave, and that's the RL4830, and then recently we brought to the market RL4835T. So any of those materials would work pretty well, and I'd probably ask anyone to go ahead and talk to our sales engineer or application development manager and just kind of tell them what you're going through and what you're looking for, and we should be able to help you pick the right material.
Okay, next question. I saw the Hall Array model for surface roughness in the Rogers software. Are those actual values for manufacturing process, and does that contain top and bottom etched or non-etched layers differently?
Yeah, in the MWI software, I put in the Hall Array model, and I really like that. It works really good, and I have numbers in there for the copper surface roughness as the Hall Array model desires and needs, and that is the SAI, surface area index, also called surface area ratio, and also the average nodule size. So those numbers are in there, and I have it in the software two different ways. One, as we measured the copper, and then two, the best fit to insertion loss. So the actual measurement is the SAI and the nodule size as we measured the copper, and many, many measurements at that. So that's actually the measurement of the copper surface itself. And then what I did was, after doing a lot of experimenting with many, many different circuits, knowing what the copper surface roughness was, then I adjusted that to have an option to where you can have the best fit for those parameters for the Hall Array model. And all that's done with the microstrip transmission lines. And when we actually measure the copper itself, we measure a raw copper foil with the laser profilometer, basically. Okay,
we've gone through most of the questions, but we'll try to get back to any that we missed. We have run out of time, so I'd like to thank John for a great presentation and Rogers for sponsoring today's webinar. You can find out more about their products at their Tech Hub and on their website. Please note this webinar has been recorded and will be available to watch within about an hour from now. You can find it in the events section of the Microwave Journal website. If you or your colleagues would benefit from watching it again or for the first time if they missed it today, please let them know about it. We thank everybody for joining us today.